All right, so we're going to review the STT unit together. And I'm just going to go through a sample problem that you might see on the final exam. And hopefully this makes some sense to you so that you could ace it on your exam day. So the scientific thinking and tools, that's what STT stands for. It's fundamentally, can you understand an experiment? Can you extrapolate some data? Can you give a conclusive statement about what that experiment is showing? So in this example, we have a pumpkin catapult that we built for the National Engineering Competition. So catapult, if you don't know, kind of works like this. You pull back and then you release, and then there are some springs that cause an object to move forward. So we're gonna pull this catapult back different distances, and as a result, the pumpkin will move forward in the horizontal direction. And our first task is to try and figure out the IV, what we changed, and that should be pretty simple. It's going to be the distance that the catapult is pulled back, and we have these different distances in meters because units are important. The DV, what do we measure? Well, that's how far the pumpkin travels. So that's our DV, pumpkin traveling distance. What should we control in this experiment? Well, we should probably control the catapult itself. We should probably control the weather, the temperature, the pressure of the air. We could probably list a few more in here. Springs in the catapult. So over time, the springs will lose their elasticity, so we want to make sure that we're using the same type of spring over and over again in our data set. So those are just a few of the things that need to be controlled in this experiment. Next, we're going to want to plot our data, and this is pretty simple if you know that on the x-axis goes your IV, on the y-axis goes your DV. So what is my IV? Well, that's distance pulled back, and that's measured in meters. And on my DV, I've got pumpkin traveling distance, also measured in meters. The key to this is to make sure that everything is standardized, so you can't just pick points and say, I want this to be 12. You need to first come up with some sort of scale. So on my IV, I need to go up to 4, so I'm going to go up by 0.5. So this will be 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and then 4. 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. And on my y-axis, I need to go up to 80, so I'm going to go up by 10s. 10, 20, 30, 40, 50, 60, 70, 80. If you want this to be more precise, I would encourage you to use a ruler. And then you're just going to find your points. So starting with this first one, 0.5, 12, go to 0.5, go to about 12, put my data point there. I'll use a different color for this. My next data point is 124, go to 1, find 24, bam, there's my next data point. 1.5 is at 38, 1.5 to 38, 2 is at 50, 2.5 is about 62, 3 is about 74, and 3.5 is 80. Those are the data points. Now we need a line of best fit. So this looks a little bit better if you circle the data points too. There's my data points. but I'm going to draw one straight line that represents all of my data. Something like that. And that would be my data chart. Now, let's say that I found the slope of this line because I used Desmos, and I found the slope to be 24.7 and the y-intercept to be 0. What do these numbers mean? We have to write a sentence with the meaning of these numbers. Well, remember back to find the slope, or the meaning of the slope, we think that the slope is rise over run. And we'll write this sentence by saying for every whatever's on the IV or x-axis, we get something that's on the y-axis. Let me write this out. For every, well, this is meter pulled back on the catapult, what happens? Well, then the pumpkin will travel our number, 24.7 meters. Pumpkin will travel 24.7 meters. Done. What's the y-intercept mean? Well, that we think about our IV being 0. So if the distance pulled back is 0, the pumpkin will travel 0 meters. That makes sense. If you don't pull this catapult back at all, the pumpkin is not going to move. So if the catapult is pulled back 0 meters, or not at all, the pumpkin will move 0 meters, or it won't move at all. Okay, the last thing in the STT unit is to make a prediction using your given information. So this is the slope, this is the y-intercept. We can use this to form a line equation. Remember y equals mx plus b? Yeah, you do. You're going to use that here. This is your m, this is your b. So your equation for the line of best fit is y equals 24.7 plus b is 0. I dropped my x. Where y is the pumpkin traveling distance and x is the distance pulled back. So let's look at this here. Y is equal to 24.7 x plus 0. And I want to, let's look at this. Predict how far the pumpkin will travel if you pull back the catapult 4.8 meters. Which means that 4.8 meters is your x. That's your distance that you pull back. So y is just 24.7 times 4.8. I'll leave you to put that into your calculator. Just remember that this is the pumpkin traveling distance. The unit is meters, so you need to put that in meters. That is STT. If you can do all the things that we just did, you are in great shape to get all those points. All right.